we're looking at just a generic situation. I'm going to say example, and this will be a central limit theorem problem. Let's say we have a class of statistics students took a test. I'm going to kind of paraphrase. Took a test and the class average was an 80 with the standard deviation of, well, I'll put down what I always go for. Whenever I design a test, I design it with the hope that there's a mean of 80 with a standard deviation of 10. And I've had it in the past where I make that comment and the student will say, now you all would have no excuse because you've had some experience with statistics, but I'd have some students that say, well, you have low expectations for us. And I'd say, well, wait a minute, let's not gloss over this, all right? Because if the mean is an 80 and the standard deviation is 10, that gets me to 100 on the high side with 2 standard deviations. And a 60 on the low side with -2 standard deviations, 2 standard deviations away from the mean. All right. Now we know that any score that's within 2 standard deviations about the mean is considered to be usual. Anything that's beyond would be considered unusual. Right. So I want 80-10 because I want it to be a usual occurrence that the scores are passing 60 or better, right? I want it to be unusual that somebody gets a failing grade, so something less than 60. And I want it to be unusual that somebody gets over 100, right? Because I look at it like, oh, you earned your 105, you know, or whatever you got. You know, like you got everything right, maybe you got a bonus problem right. Like I don't want everybody to do that. I want you to feel special when you do that. Right? It's the worst feeling in the world. Not the worst feeling. There's always worse. But it's pretty rough feeling when you get a score, let's say you get 100 and you find out everybody else got 105. It's like, even when I succeed, I fail. You know, like you don't feel very good at all. You know, like that it's a hollow victory. All right. So I have a class of stat students. They took a test with a class and the class average was an 80 with a standard deviation of 10. All right. So what I want to do is find the probability that a group of 10 students at a mean less than 60. And we'll say mean grade. All right. And that's a pretty important question, at least from a teacher standpoint, because I always like to have the data to come back at somebody when they say, everybody failed this test. I usually say, I'm kind of a wise guy. If somebody comes at me with something like, everybody failed this test, I'm like, in my mind, I'm like, no, everybody did not fail the test, because if everybody failed the test, I would give a redo. I would curve it. I would do something. You know, like if everybody failed the test, there would be some sort of measure taking. All right. So what I usually say to the student is like, no, everybody didn't fail it. Just you and your 9 closest friends did. You know, and so that's all that happened. You know, and usually it's all anecdotal. You know, you finish a test, especially when it's in person. you're leaving the room, you see your buds outside in the hall, and you say, oh man, that test was a rough one. And you're kind of hoping they say the same thing because you don't want to be the only person that did poorly. So they say, yeah, that was tough. I did so bad. And then you just walk away being like, everybody in your world failed the test. Not everybody failed the test. Everybody in your world failed the test, but it feels like everybody failed the test. All right. So let's investigate and see if that's actually what happened. All right. See what the chances are that a group of 10 students would have a mean grade less than 60. All right. So first thing I would want to do is identify this as a central limit theorem problem. Because we are asked about a group of people. Now, it doesn't always, as you know, it doesn't always have to be a people. It does have to be a group in order to be a central limit theorem problem, but it doesn't always have to be specifically people. It could be, like wattage of a group of 10 light bulbs or something like that, right? But we're asked about a group of 10 people specifically, and their averages, the mean, all right? So the fact that it's a mean and a group, that's what's dictating that it's central limit theorem. All right. The biggest problem that people have had over the course of my career anyway, when it comes to this concept, is knowing when it's central limit theorem and when it's not. All right. So you have that n value. And generally, I mean, I suppose it is possible. You've seen it before where you're given word problems, and in stat, it seems like everything is a word problem. But you're given some situations where, like all the information in the problem fits a formula, right, perfectly. And then there's some kind of word problems where you have extraneous information in the problem where it's like, oh, I didn't need that. It was just there as a distraction. You don't like that. I can tell you that for the material in this topic, there won't be any extraneous information, right? So you get an n value, right on over here, group of 10 students, that's an n. All right. So we're talking about a group of individuals, aside from the fact that it flat out says group in the way the problem was structured. Even if it didn't, you could say a cohort, pretty popular word these days, cohort of 10 students. Like it's still 10 whatever. That's your n value. All right. So those are the key indicators that it's a central limit theorem problem. So what I would do is identify the mu sub x bar and the sigma sub x bar. All right. Mu sub x bar is always the same as mu. All right. So the class of stat students that took a test, we're defining that group of individuals, the people who took the test. That's the population that we care about. That's the relevant population. All right. We can define anything that we want as a sample or a population. If I were trying to draw a conclusion about all students at WCC, then this would be a sample. But all I care about is how these 10 students did compared to the other students in the class. Those other students in the class constitute a population. So that gives me license to call this 80 the mu, which we know is going to be the same as mu sub x bar. So I got my 80. The standard deviation, once I designate that 80 as a mu, that automatically makes the 10 a sigma. All right. So sigma sub x bar is equal to sigma divided by the square root of n. So 10 over the square root of 10. All right. So not really a clean computation, but we don't actually have to do the computation. We'll let Desmos do it for us. All right. Speaking of Desmos, what I'm going to do at this moment is I'm going to hijack my own class here real quick. And just make sure I have the right screen up. I had this awful habit recently of having the wrong thing up on the screen during Zoom sessions. That sounded a lot worse than it is. I'm talking grades. You know, like student information. It's like, dang it, now I got to delete that video, you know, so it's like sensitive information. Okay, anyway, so I'm going to share my screen on this end. Yeah, I'm going to cut off that share and I'm going to start this share. So what I did, because I had this announcement with the normal curve area, but I got a little ambitious last night with Blackboard, and I created a link on the left-hand side, right below tech assignments, right above online meetings. You might have seen it because you got to go to the online meetings to get here in most cases. So right above that, you see calculators. You click on that, and I made a bunch of different, well, a few different calculators. All right, and some of them were ones that we've talked about before. Some of them were the, as promised, the modified ones that I said that I would do. You know, I eventually do everything that I need to do. It's just sometimes it takes a little while. So if you click on the normal PDF calculator, well, on your end, it'll look fine. On my end, I have to go into student view and then do it again. It brings up a normal curve calculator, which has all the stuff that I've been kind of referring to. All right, just I cleaned it up a lot. So, you know, finding area under the curve, under the normal curve given a z-score, I created it as a folder. When you hit that drop down, you see that it asks you for, I change it from A and B to Z min and Z max. I thought that made a little bit more sense. All right, the minimum Z value and the maximum Z value that you care about. And then it'll spit out the area related to that. So you could test it out. -3 to 3 should give you about 0.997, 99.7%, as we know from the empirical rule. If you want to make it a little bit more obvious, just go from something like -10 to 0. And you see that it gives you a 0.5. That's half the curve. Now you might be wondering what that extra little bit of fluff is there. So let me close up this folder and open this one, which is finding a z-score given the area under the normal curve. All right, and you see I have another graph here. All right, this other graph is when we're going the other way and we're trying to find the z-score corresponding to a particular area. So you could turn that on or off if you want. I put it in there as I figured why not, but it's an extra bit of verification to make sure that this number is right. But basically it's, you have the area to the left. So let's say you know that it's 0.5 to the left of a particular z-score, but you need to know what the z-score is. So you change that to 0.5 and you see that that corresponds with a z-score of 0. So what you can do is toggle back here, turn off this graph so that it's not distracting you, and then go in here and turn this one on, and you can see that it corresponds with the appropriate area and the z-score. So let's say I wanted to go out to 1 standard deviation. I don't know where 1 standard deviation is, except to say that it's somewhere in this neighborhood. You know, somewhere along those lines, you know, it gives me a z-score in the neighborhood of 1 standard deviation, corresponds with an area, and then it plots the graph for you. It's up to you. Again, if you want, you just get rid of this, just click it right out. You know, this is yours. So what I recommend is that, you know, these are all on Blackboard, and they're always going to be in their original form on Blackboard. so I'm not going to edit them and update them or anything like that. They're just the way they are. So if you want, you click on a little waffle, log in, and save these bad boys for yourself. Right? I think that's probably the better way to go. I look at these calculators as like a nice starting point. Right? So it's what you do with them from there on out that's going to be kind of a determining factor of whether or not you're going to find a lot of use out of this. So if you look at this and say, well, I don't like this graph, well, save it and then hit that little X and get rid of it. You know, it's yours to keep, right? I get you started. You go the rest of the way. And that last one, to solve for X, because I know that when we were solving for the value of X, after coming up with a z-score, it was kind of like, oh, we did some algebra. I didn't sign up for this class to do algebra. I don't want to do algebra. So I included this here so that you didn't have to do the algebra. And I mentioned that that I had a capital M and an S in here because I wasn't using the right software to get the mu and the sigma. I fixed that, so it makes it a little bit more obvious. But what this does is it calls back to the previous Z value. So in that previous folder, when you determine what Z is, right? So it tells you what Z is here, it hangs on to that. And then it pops it in here so that you can get the X value that goes along with it based off of a mu and a sigma. All right. So, you know, it's up to you. You know, you may or may not find value in this. I hope that you do find some value in it because I put in a little bit of work. Yeah, I did this with the thought of being helpful. So if you find it not to be useful, if you think it sucks, it's terrible, then certainly don't tell me that, because like I said, I did a fair amount of work to get this. All right, so I'm going to go back to my other display, and we'll kind of use these. The reason I mentioned it is so that we can use it to answer the problem, all right, or answer the question. Oh yeah, no problem. I appreciate that. So I'm going to share this screen. All right. So now I want to get into my computational stuff here, and so I can use my my area under the curve. I have an area under the normal curve, but it's the same thing. All right. So let me just make sure it's the right version. It is. So in order to find the relevant area, I'm going to need some computations. All right. But nothing too crazy. It's just the z-score going on here. All right. So the z-score, and again, we're looking for a mean grade less than 60. So the first thing I would do is I'd write it in, normal terms, symbolic form, nothing in terms of the central limit theorem. I'd say X bar has to be less than 60. All right, because these people said that we all failed. Well, I don't think you did. All right, so I need to find the z-score that goes along with that. So X bar minus mu sub X bar over sigma sub X bar. That's going to be 60 minus 80 over 10 over the square root of 10. All right. So in my calculator, just in a random field, it doesn't matter where, because you don't even need to hang on to this computation. Division bar, 60 minus 80. Another division bar, 10 over the root of 10. And it'll give you the value, the relevant value. So, and all we need is a decimal approximation of it. So 3 significant. So negative 6.325. All right. So what that tells me is that this guy right here corresponds to the probability that Z is less than negative 6.325. Now, if you're developing a decent sense of this normal distribution stuff, you should know that the probabilities get more extreme the further you get away from zero. Right? So you just have that in mind. Area under the normal curve, given a z-score, my minimum value should be something really small. -10 is fine. Right? My maximum value, and again, you can turn off the other graph. Right? So I'll turn that one off. So I'm only focusing on the one that really matters. All right. So we're looking at -6 and change. So I'm not going to be able to scroll to that. So all I'll do is just type it in. -6.325. All right. Now you can see that there's no shading there. And you say, okay, well, what did I do wrong? I don't see any shading. That's good to know. I had no idea. No, I honestly, it's right up until this moment, because I'm doing a dual screen. I never knew whether or not my mouse actually showed up on the screen, but it does, and that's very distracting. All right, so I'm going to try not to do that. So that gives me this probability. I'll move this over. We're talking 1.266 times 10 to the -10th power. All right. So if you're wondering, that's the same as saying 0.00000, that's 5 zeros, 6, 7, 8, 9 zeros, 1, 2, 6, 6. All right. So that probability is very, very small, infinitesimal, right? To the point where it's like, it might as well be zero, right? Very, very teensy tiny, right? So what that tells me is that it's extremely unlikely, borderline impossible, for a group of 10 students to fail a test under these circumstances. All right. So now you get greedy and you say, well, what about a group of 2? What about a group of 3? What about a group of 4? You know, like what are our different possible probabilities here? You play around with the numbers, but you get the idea that having just a single person fail is kind of it's unusual / unlikely, because it's outside of the ±2 standard deviation interval. But to have a group of more than one individual, so 2, 3, 4 individuals, the more individuals you throw into that group, the more unlikely it becomes. Right? So very, very, very rare outcome. Right? So I don't know how many teachers think like this, but when a student comes to me and says everybody failed the test, you know, there's the usual reaction of, well, no, that's not what happened, because I know what the data is. But I also look at it from the statistical standpoint of like, oh, that sounds like a problem we can go over in class, because that's certainly not the way it would ever play out. All right. So so yeah, it's definitely an interesting case. And really, I mean, we're looking at it in the context of test grades. Okay, well, how about contracting a virus? You know, you have a group of 20 people, 100 people. You want to get into the probability. If you have a sense of the probabilities, you know, like if you know what the probability is for a single person to catch a virus, then you can start getting into what the probability is for a group of individuals to catch a virus and what the average likelihood would be. You know, so these are some possible applications that you could be looking into. And you know, there's a lot going on there. You know, it's a lot of extra variables that need to be accounted for. So it's not as simple as, you know, like, did you study or not, you know, but it's definitely worth investigating. All right. So that brings us to this concept of the design of a study, which it's actually a pretty good segue into this really important concept. It's also kind of interesting and funny and everything, all the above. When I first started teaching this, and I think to some extent still, this was sort of an optional topic. It was an if time. If you had enough time in the course and you could get around to it, then you could go ahead and teach this part of it. And it's like, this is the most important part of statistical analyses. If you don't have a well-designed study, then you're not doing anything right, you know? So what we're gonna do is we're gonna take some time and get into how you collect data appropriately, because we've explored pretty much from every aspect, believe it or not, how you can analyze data. We looked at it from a graphical sense. We looked at it from a numerical sense, the idea of finding means and standard deviations, and regression analysis and stuff like that. We found probabilities, you know, some obviously more complicated than others. You know, some probabilities were, you know, we're talking about flipping coins and rolling a die. But then we got into the normal distribution and the central limit theorem, which talks about larger data sets and samples. But we never really talked about how you go about collecting data to begin with, and when it's appropriate to collect what type of data. So that's the importance of this stuff. And I would even say that if you were to gain anything from this class, it's probably meaningful in your life. It's probably going to come from the next few pages. All right. That's how you can read through and sift through the BS, you know, perpetrated by others, because it's abundant. You see it all the time, whether it's in the news or you're reading something online. I just had students complete an assignment in my AP Stat class in the high school on misleading graphs. So what I wanted them to do is just go online, or, you know, find a publication that had a graph that was misleading. Whether it was intentional or otherwise was not important. It was just the idea that they were looking for a graph that was designed to get people to think in a certain way, you know. And, you know, surprisingly or unsurprisingly, depending on how you look at things, they all kind of sort of went in the same direction, in that, you know, like there was a lot of politics involved, you know, so they were looking at like different media outlets and such. And invariably what I was seeing was a lot of students taking the misleading graph, because I told them that part of the assignment was to make it not misleading. Take that graph, change it so that it's more objective. And so they did that. They changed the graph. The problem was
Why?
they misleading.
The game?
The PC.
Oh,
Oh, okay.
Oh,
That just took the wind out of my sails. I don't know what just happened.
Wait, what? What just happened?
Well, somebody just started talking really loudly, and I was in the middle of a sentence, so I lost my train of thought. And so I don't know.
You were talking about redoing the graphs. Your students submitted graphs. They chose political graphs, and I think the assignment was rebias them so that they're a little more neutral.
Right. Okay. Thank you. So yeah, and so what they invariably did was they revised them, but they went the other way. You know, so instead of making them biased in one direction, they made the graphs biased in another direction. So if it was left leaning, they made it right leaning. If it was right leaning, they made it left leaning. In almost no cases did the students make the graphs completely neutral and unbiased, right? And that has to do with the inherent bias that exists within the non-random nature of existence, right? Because one thing that we're going to have to do is we're going to have to kind of think in terms of, statistical vocabulary as being different from the kind of vocabulary that you'd use in real life. Like, for example, just the word random. Like if somebody were to say, that's so random. Well, they're not using the term properly, but it's sort of nitpicky to say, well, you're not really using that term the right way, because then you become you're kind of a jerk, so you don't call people out every time they misspeak or they use a term slightly incorrectly, if you get the gist of what they're saying. But yeah, like, that's so random. Well, what was so random about it? Because you were not expecting it? Well, that doesn't make it random. Random means that there was a complete and utter lack of influence involved, right? Which means that the outcome was determined solely by chance and chance alone, no other influence, right? So it might be unexpected to you. It might even be random to you, but it's not random by nature, right? And the same idea goes for bias, because we look at the term bias as, another variation of it could be prejudiced. You look at it and say, well, there's some dastardly motivation here. The definition of bias in a mathematical sense, in pure mathematical sense, is not random. All right. So information, whether it's numerical or qualitative, that information, if it's collected in a way that is not completely randomized, then there is automatically bias included. All right. So when you're collecting information, like if, for example, a survey, you're standing in the middle of the mall, whatever mall, and you want to collect information from different individuals as they're passing by. So you flag the first person down that you see. All right. Why did you flag that person down? If you can answer that question, it's biased. All right. So unless it was determined strictly by randomization, then there's going to be bias introduced. All right. So why did you pick that person? Well, it looked like the first person that wasn't going to beat the crap out of me for asking a survey question as they're trying to shop with their family in the middle of the mall. All right. Oh, biased. All right. So that's one aspect. Another aspect would be, all right, well, why did you go at the time that you went? Like when you're collecting information for a survey, you're interviewing people. Why did you go at 4 p.m. on a Tuesday? Why didn't you go at 3 p.m. on a Friday? Well, I don't want to do anything on Fridays. I want to relax. So I get all my work out of the way on Tuesdays. All right, well, there's bias. Because guess what? Other people want to get their work out of the way on Tuesdays, so they're probably less likely to go to the mall or other kind of leisure activities because they're too busy working. All right. So you just introduce bias. If the circumstances by which you make your selections is not strictly determined based off of chance, meaning you use a random generator, and we've done that before in the tech assignment. We used a random generator to collect values, outcomes of rolls of dice, 500 of them, in fact. Who's to say that we can't, instead of making the parameters 1 to 6, how about, we'll keep it to the daylight hours, like 8 to 5, 8 a.m. to 5 p.m. So instead of cycling back and, hitting 1, 2, 3, 4, and 5 in the PM hours, you might go hour 13, 14, 15, 16, 17, and 18. But you can randomly select the time, and that would dictate when you would go and collect your information. Now it's random. Now it's unbiased. All right. What we try to do is kind of marry the two ideas. What ends up being the case is that, practically speaking, we can't always allow for randomness to rule our lives, because if I got to get this data collected, I got to get this data collected. The random calculator says that I have to do it at 9 a.m. Problem is I'm working at 9 a.m. So what do I do? What we try to do is we use appropriate statistical techniques to allow us to, within a certain margin of error, to draw conclusions based off of even slightly biased information with a reasonable degree of certainty, right? So there's a lot going on, but it does have and does always come back to the concept of randomness, right? If there is no randomness in your data selection, then your data selection is flawed, right? And it's as simple as that, right? Yeah, anytime you're polling people, collecting information related to that sort of thing, that you're always going to run that risk, right? So we definitely have to be careful. All right. So design of a study, we have the census. I mean, some vocabulary, pretty straightforward stuff. Census is, this is a census year. So a lot of us have experience with that. You know, it's a collection of data from every member of a population. All right. So, but we've already talked about the idea that we could define populations any way we want, as long as we have a good reason for it. All right. So if I define my population as the students in this class, then the individuals that make up that population would be everybody who's listed on my roster, right? But if I wanted to define the population as the students at WCC, then this class becomes the sample, all right? So that's a little bit of a different take on the same concept, all right? Individuals, not necessarily referring to people. Like we've talked about that before also. When we talk about an individual, it could be I used light bulb as an example before, but it could be anything. All right. Parameters are numerical values that describe populations. Statistics, numerical values that describe samples. Pretty straightforward. P, the letter P for population, the letter P for parameter. Letter P for sample, letter P for statistics, all right? It's a good correlation there. Also, you kind of think about this course, what have we been working with so far? Mostly samples, a little bit with population stuff, but mostly samples. So we have a lot of experience with that, and the course is called statistics, so there you go. All right, what we're gonna be doing is trying to use information from samples. And really, that's the foundation of all of statistics. Use information about samples to draw conclusions about parameters or populations. So, I'm seeing in the chat that people are having trouble getting those Desmos. What I'll do is I'll paste the individual links in there so that you can just copy paste it and you can get it that way. I'll do that after class. All right, because we're not going to need that any further for the rest of this session. In fact, so types of data, quantitative, qualitative. So the qualitative stuff we've kind of dealt with, kind of to overuse a term, anecdotally, a little hand waving. When you're talking about qualitative data, it's like categorical. You're talking about grouping based off of hair color, existence of hair, gender, age groupings, anything that you would use as a distinguishing factor between different groups. All right. Whether you're a humanities major or a math science major or nursing major or business administration, tech, whatever major you can think of, categorizing based off your major, right? But there is a way that even with qualitative data that we can look at possibly ranking that information. So, but that does introduce, I'll call it bias, but it's really more like subjectivity, because we would say, okay, well, wait a minute. I'm trying to think of a good, and I was going to say a good example. I'm going to say an example that's not going to piss people off. I'll be self-deprecating here. If you're going pre-med versus education route, like you're going to be a neurosurgeon, you're going to make a lot more money than a math teacher in most cases. Right? I mean, unless you're a terrible neurosurgeon and you don't get any patients that are willing to let you operate on them, yeah, odds are you're going to make more money than a math teacher, right? Even, you know, university level, whatever. So in that case, you might rank the pre-med major above the School of Education major, for example. You know, but that's based off some predetermined criteria that you'd have to be kind of clear and upfront about. All right. And it's specific to the fact that you're talking about, you know, earning potential down the line. Right. Yeah, it's basically the rules of the game. You know, so when you determine what information you're collecting, you have to be clear about how you're collecting that information. Yeah, but also what type of information that is, because that's going to dictate what form of analysis is going to be most appropriate. Right? When you're dealing with quantitative data, we've done that a ton throughout the course. You have two types. You have your discrete data and you have your continuous data. The discrete data is your countable information. Your continuous data is the data that you would need some sort of measuring device to determine the value of. We talked about that before. You're talking about time, length, distance, weight, anything, you know, like temperature. You need a thermometer for temperature, air pressure, you know, whether it's you know, like tire pressure, for example, if you're measuring that in PSI, or a barometric pressure or something along those lines. But you need some sort of measuring instrument to determine those values, right? So it's not so much a matter of saying, oh, it's this many. You know, you need some sort of device to determine its value. Now, the more sophisticated device, the more accurate your measurement's going to be. So if you're counting off time by, you know, 1 Mississippi, 2 Mississippi, 3 Mississippi, and so on, versus a stopwatch versus an atomic clock versus, you know, like whatever, you know, you're going to get differing degrees of accuracy, right? Same idea with length. If you're measuring the distance between 2 points using a tape measure, that's going to be a lot more accurate than me, you know, counting how many paces it took for me to get from one location to another. It took like 10 steps to get there. All right, well, my foot is exactly 12 inches long. Well, my left foot anyway. So, all right, 10 steps, that's 120 inches. So we're good to go. You know, I can get the measurement, but it's not going to be as precise as a tape measure, obviously. All right. So those are some things that go in the category of continuous data, right? So when I say it's uncountable, I'm not saying you can't determine its value. I'm saying that it's not something you can determine its value based simply on counting, right? Now, once you've decided on, you know, what your study is going to be, you're collecting data, you're analyzing, you're considering analyzing data, you want to have a blueprint in order to conduct that analysis, because we've gone through a lot of things in this course. We've created graphs, we got histograms, we got box plots, we got scatter plots. We, like I said before, we did measures of center. We've done correlation and quantile plots and probability plots and all that stuff. You kind of look at it and say, well, what makes sense based off of the information I have here? Well, the first step in making that determination is figuring out what type of data you're working with in terms of the classification, because certain things fall in certain categories. So you have your nominal level, your ordinal level, interval, and ratio levels, right? The nominal level, you know, the definition there says consists of names, categories, blah, blah, blah. I just remember, or I used to remember it anyway, now it's just muscle memory, but I would remember the gnome part of it because I took French back in the day for many years, meaning 5 years. So 1 year in middle school. Actually, no, I did some in college too. I want to be fair about this. So about 6 years of French, which means that that I really can't have a conversation with anybody, but I can recognize some words here and there. It's like, oh, I remember learning that word that one time. Right? But one of the words that I remember, because it was on the top of every worksheet that I ever completed, was nom, which is name in French, en français. That's another thing I remember. Right? And oh, of course, je m'appelle Ted. So the nom part stuck out to me when I see nominal, because that resembles name in French, you know. And so, hey, guess what? The definition for nominal level is consists of names, labels, categories only, and you can't assign numerical values. All right. Now, that little part there at the end where I say can't assign numerical values, it's not entirely true. I want to clarify that, but there's really, I really can't think of any other way to state this except to say you can't assign numerical values. So what I say kind of as an add-on is, or you can assign numerical values. So, or you're assigned, oh, I'm making that super tiny. I don't know why. This is going to seem weird. Or the assigned numerical values have no numerical value. That, I think that goes under the category of officially the weirdest thing that I wrote down as an explanation or a definition, at least this week. Intentionally the weirdest thing. There's some things that I write, I'm like, I don't even know where that came from. What this is saying is, let's say, for example, you have a list of students, for example. I always tend to go back to that. So a list of students, and you want to organize them by gender. All right. You have an Excel spreadsheet, and instead of just going through and saying, all right, male, female, you label the males as 0 and the females as 1. And Excel is pretty powerful. So you can, it can sort alphabetically, it can sort in a bunch of different ways, right? But you decided that, you know what, I'm going to keep it simple. I'm going to let any of the males be represented by the number 0, and I'm going to let any of the females be represented by the number 1. That doesn't mean that males are worthless, all right? If you think that, that's a personal belief, that's a different story. But the bottom line is, you can't say that females are worth exactly 1 unit, you know, like, and males are worth 0 units. That's not how it works, all right? So we just leave it as, okay, like placeholders or labels to represent the particular categories, but they don't have any meaning besides being just labels. All right. So when I say we're assigning numerical values, but those numerical values have no numerical value, I really mean that. And I mean, it's actually kind of fun to say it, but you know, I can also see how that might be confusing. All right. So if I wanted to say freshmen, sophomore, juniors, and seniors in the high school level, 1, 2, 3, and 4. All right. 1 for freshmen, 2 for sophomores, 3 for juniors, and 4 for seniors. That doesn't mean that the seniors are 4 times as awesome as the freshmen. You know, it's a matter of perspective. All right. The ordinal level is, it's a designation still, but you can assign numerical values to individuals within a data set, and they can be arranged in some kind of order. So in the case of what I just said about freshmen, sophomore, juniors, and seniors, the numbers 1, 2, 3, and 4 would represent labels, absolutely, but we could also put them in order, because 1 would be the lowest level age-wise, and 4 would be the highest level. But in terms of, what does that mean? Well, it's still labels. Now, if I tell you that that 1 represents the first year of high school, now we've kind of graduated to a different category. It's beyond labels. It actually has a numerical meaning. But that's also something that we'd have to designate, and describe as a side piece of information. All right. But if you can have data that can be arranged in order, but the differences between data values, and I'll just read it, can't be determined or are meaningless. It's a weird one to think about. Then it would be in the ordinal level. So it's really just for sorting. All right. So if you wanted to, for example, take the students, and I actually have this, it's in my spreadsheet, my roster, my attendance roster. I have all your names listed in alphabetical order by last name. And in the spreadsheet, right next to your names is a number, right? And it's built into Excel. It's cell A1, A2, A3. So you're all in column A, and you have, the different rows corresponding with your placement within the spreadsheet, right? So the first student in the class is in cell 1. So you're in position 1. You're the first student. The last student is whatever, number 29, number 30, but that's all that is. It's not a ranking. It's not based off of any criteria other than the alphabetical order of your names, right? So it helps me put you in alphabetical order. It's a sorting mechanism, but it doesn't mean anything more than that. Like if I took the number 13 and subtracted from the number 3, right? So the 13th student minus the third student, what does that give me? It doesn't really give me anything meaningful. It doesn't mean that if I subtract one student from another, I'm going to get what? What does that 10 mean? All it does is it indicates position, but that doesn't give me anything in terms of the meaning of the values. All right, so that's an example of ordinal. If you can determine meaningful differences between values, then you would be at the interval level. And then the last one would be the ratio level. The difference between interval and ratio level is whether or not 0 can be in the set. All right. Now, at this point, we kind of look at these terms and saying, well, now it's starting to get a little out there. What does it mean for 0 to be in the set or not be in the set? That's kind of weird. All right. So now it's time to get into some examples and kind of take a look real quick and see what's going on. So the first example, and I think my favorite one, although I'm kind of partial to number 4 also, but they're pretty good examples. These are my exemplar problems. These are like my favorite ones to kind of get across the idea of the NOIR, nominal, ordinal, interval, or ratio. Noir. So anyway, letter grades. Sorry, just to really drive that home. If I'm going to classify them as nominal, ordinal, interval, or ratio, there's some things that you can kind of dismiss immediately. And by the way, this lends itself beautifully to multiple choice questions on the test, in case you're wonderful. In case you're wondering. I almost said in case you're wonderful. You're all wonderful. So my letter grades, at least in this school, and this is a good opportunity to talk about this because not everybody knows this. I'll go low to high. All right. So F on the low end. And I'm assuming grades that you can get rather than ones that show that you didn't complete a class, like incomplete or W's and things like that. F, D, C, C plus.
Professor Ken?
Yeah.
I'm so sorry. I can't, I'm not even listening. I just received a message from my daughter's school that I have to quarantine because she was exposed to COVID. But no, my mind, I don't, I'm so anxious right now. I don't know what to do. Is this, can I record, I'm so sorry. I'm just nervous.
I always record the lessons and post them on YouTube. So it'll be available to you.
Yeah, because they just sent me 2 emails and she's asthmatic. I really don't even know what to do right now. I'm gonna have to go take her to get tested early in the morning.
Yeah, definitely. That's number one. And also,
Mm.
it looks like a lot of schools are going to be shutting down pretty soon anyway.
Mm.
What do they
Yeah,
say?
New York City schools just shut down.
Yeah,
Yeah.
but she goes to an independent school and she had lunch with this kid because they're friends. And then she texted her, "I'm so sorry, Destiny, I'm positive. I know the school just send me email. I'm so scared because she's very asthmatic. Her lungs is no good."
I'm sorry to hear that.
Oh gosh.
If you got to go, that's fine. Yeah, like I said, this is getting posted, so you'll have access to it all.
Thank you so much. I'm gonna see if I could call around and see if I could get an early morning testing for her to go take her tested.
I've been doing all right with Glen Island. If you want to look there in New Rochelle, it hasn't been a long wait, and it's a drive up. So you don't even get out of your car. And
Okay,
it's,
good. I'm gonna try that. And how long do it takes to get the results back though?
let's see. I went on Saturday and I got it today, so it was a few days. It was like 4 days.
Okay, I
But
think I'm gonna try that. But she wants it immediately because she's so scared.
yeah,
Yeah.
I mean they have the rapid ones, but those are kind of tricky because sometimes they give you false readings, and that's the last thing you want, like to be told that you have it and you don't.
I
So,
know she's scared. She's crying, and I'm so
poor
worried.
thing.
I'm gonna take her to get tested tomorrow, but I'm gonna see if I could talk to her because I'm disoriented right now. When things happen to your kids, it drives you crazy.
Yeah, that's it's like the number one.
Thank you so much.
No problem. Take it easy. Yeah, it's just one of those things. Like when things happen to you, it's you can kind of handle it, but then when it happens to somebody you really care about, it's almost like there's the powerless feeling. It's like you just put on the earth to watch it all happen. It's pretty rough. Yeah, so anyway, the letter grades, we have F, D, C, and C plus. Also, that would be terrible if that was the maximum grade that you can get. So we got the B, and we got the B plus, and we got the A. All right. For those of you who are new to the school or just not familiar, we don't do minuses here. Right. So that's not really particular to this question. I just figured I would throw that in there because that has come up in the past. It's like, what do I have to do to get a C minus? Like, oh, well, nothing, because I can't give you that. That's not an option. Right. So when we're categorizing our letter grades here, well, we know it's certainly not nominal, right? Because that would be names, labels, categories only, right? So that would be like classifying people based off of gender or age group or something like that, with no meaning other than the fact that you're in one group or as opposed to another. It's like if we were doing group work in this class, and I say, okay, get into groups of 3, no one group is better than any other group, at least that, until you turn in a product. So that's not what's happening here. The order matters. Like if you're in the F group, you're not a happy camper. If you're in the A group, you're thrilled. All right. So it's definitely not nominal. All right. So what I like to do is just kind of off on the side here is I just write NOIR, N-O-I-R, nominal, ordinal, interval, ratio. And as I kind of conclude to myself which one it is or isn't, I just do a quick, it's not that one. All right. Now, ordinal would be, you could put it in order. So that's certainly true. But the differences between data values are either cannot be determined or meaningless. All right. So now we get into some gray area. And the good thing about these kind of problems is gray area is sort of encouraged, because that gives you an opportunity to maybe draw a conclusion that is different from what I might draw as a conclusion, but if you have a valid reason, it's still correct. Right? So I look at this and I say, all right, well, just these letters, I can put them in order. I know that D is better than F, C is better than D, C plus, and so on. All right. How do I find the difference? Well, can I do something, for example, like D minus C? Can I do an A minus B? All right, so it doesn't seem like I'm able to draw a conclusion here as, you know, what is the letter A minus the letter B? Now, if I assign GPAs to this, that's a different story, because then I can actually get a subtraction. I can get some results. But even then, it's still going to be some gray area. I'll explain that in a second. All right, so far I'm leaning towards ordinal. All right, but now let's say I throw in some GPAs. All right, I know the corresponding GPA, GRA? No, GPA. For F is a 0. You get no credit for a 0. For an F, other statement was true, but specifically the F. 1 credit, or 1 credit per credit hour for a D. Right, so per 4 credit hours, or whatever number of credit hours. 2 for a C, 2.5 for a C plus, 3, 3.5, and 4. All right. So now with that in mind, maybe I could say, all right, well, maybe I can't figure out what a D minus a C is. Even with the GPAs, I still can't, because that would be like saying a 1 minus 2 is equal to a negative 1. I don't know if I'm deriving too much meaning from that. All right. But a 4 minus a 3. That would be equal to a 1. Okay, so then I correlate that with what the 4 represents. Again, that's an A. The 3 represents a B. So the 1, that corresponds with a D. Okay, so you kind of look at it this way, and your belief in the answer to what I'm about to pose will determine whether or not this is going to advance beyond the ordinal level. So let's say it's the end of the course, roughly, you know, like a week or 2 to go. Or maybe you're going into the last unit test or the final exam, and you're carrying a B average. All right, so you're pulling a B all the way up until the final exam. And you want to know what you got to do in order to get an A in the class. Is it reasonable to expect that getting a D on the final exam would get you an A for the class? You know, you're carrying a B. All you got to do is D work in order to get your B up to an A. That's not really likely. Another more obvious example, I think, is the idea that if a C is weighted as a 2, we know an A is weighted as a 4. All right. What that would imply is that C plus C is equal to A, right? 2 C's equals an A. Right? It says it right there. You got 2 2s. You take 2 C's. That's 2 2s. That gets you to a 4. All right. That makes sense. All right. So let's say you're one of those 13th graders. I always get a few of those. You just started college. You know, you finished high school. Maybe you're still in high school mode. That's the 13th. That's what 13th grade means. It's a college student who's still in high school mode. Right. So at the end of the first semester, you think you're off the hook. The parents aren't going to bug you anymore about grades and things like that. But you find out that they most certainly are, because now it's not free public education. Now they're paying for you to go to school. So when you were not doing so hot in high school, they were like, well, at least we're not paying any money for it. Now they're paying money for it. They're like, you damn well better be doing good work. So you come home, they want to look at your grades for the first semester. And you say, hey, listen, relax. I know I didn't get any A's, but I got 2 C's. 2 C's equal an A. They're not happy. That's not going to make them laugh. All right. So And that's because 2 C's, I mean, you can tell anybody you want, I got 2 C's. Oh, just do me a favor, registrar. You see those 2 C's I got? Just take those out, merge that into one class, and let's just call it an A. It's not how it works. All right. So I don't think, and I don't think anybody in here would necessarily argue with it, that we can advance beyond the ordinal level here. All right. So this is going to be an ordinal set of data. All right. The gender case was actually my prime example for something that would be nominal. So that one doesn't even require any explanation. That's going to be nominal. All right. Number 3, weight in carats of diamonds. All right. I only learned recently that carat with a C is for gemstones and carat with a K is for proportion of pure gold. I had no idea. I knew that there were different spellings, but I just thought it was like choice, you know, like the British spelling of something, like recognize with an S as opposed to a Z. Like I thought that's what it was. I had no idea, but apparently this is what it is. So the weight in carats of diamonds. So again, noir. Well, if I tell you that you have, that I'm, you know, it's an engagement ring and I'm going to get you a 1 carat diamond as opposed to a 3 carat diamond, I don't think you're looking at those as being just categorical. You know, just like, oh, it's just a name, a rose by any other name. No, it's like one's bigger than the other, right? One's a lot bigger than the other, right? So it's definitely not nominal. Ordinal would be just putting it in order, but the differences in values not having meaning, right? So let's say, for example, again, I got 1 carat versus 2 carats versus 3 carats, all right? If I were to take the 3 carats, the 3 carat diamond, and subtract from it 1 carat, I would get 2 carats. That would be meaningful. Now, I don't work with gemstones, so I'm pretty sure this isn't how it works, though. I don't think you could chop off 1 carat worth of diamond and be like, well, here's your 2 carat diamond, and have it have the same value as an authentic 2 carat diamond. It's gonna, if you chop off part of a diamond, if you like crack that bad boy open, first off, it's probably not really the diamond because the density of it. Like, if I'm able to crack that diamond, then it's either really not a pure stone, or I'm just like incredibly powerful. But odds are the purity, the shape, the cut, the color, all that, the clarity, all that good stuff is going to be impacted. All right, so it's not going to be as nice. But just going by the weights, yeah, if I chop off 1 carat worth of diamond, then from 3 carats, I'm going to have 2 carats left over. That makes sense. Again, it's not something that would be appealing, but it would mathematically work out. So that gets us beyond the ordinal level. So then it's a debate between interval or ratio level. So the debate here really lies in the fact of, or the possibility that 0 could be in the set. All right. So then I would look at this and say, well, a 0 carat diamond, I would think that means no diamond. All right. If I have a 0 carat diamond, then I would think that that most likely means that there's no diamond at all. Right. So I would call this the interval level, because I would not want to have a 0 carat diamond in my set. Right. Now, there are exceptions, because you could look at it if somebody were rounding, you had like a 0.18 of a diamond. I'm sorry, 0.18 of a carat. You could say, well, that rounds to 0 if you're rounding to the nearest carat. So yeah, that's the gray area I was talking about, because you can make a case that this would be the ratio level, but you'd have to further explain. You'd have to say, well, based off rounding. I had one student that made an argument, and it was a valid argument. He said, well, in order for a weight to be a weight, because they're physics oriented or physics minded, they looked at it and they said, well, in order for there to be weight, there has to be gravity, right? So if you have a diamond in a place where there's no gravity, so out in deep space, then it would have no weight. So therefore it's ratio. Like, all right, you win, full credit. You know, there are exceptions, but that gray area allows you to make your case, and if your case makes sense, then you still get full credit on it. Same idea for body temperature. So we're looking at, you know, a lot of different possibilities. When we're talking about body temperature, it could be a question of whether or not it's in Celsius or Fahrenheit or Kelvin scale. It could be, you know, or what kind of body are we talking about? Human body? Are we talking about a lizard? You know, what are we working with in terms of like, is the individual living or dead? Like, what are the possibilities? So when I look at nominal, ordinal, interval, or ratio, I know that temperatures follow a particular scale, and that if an object is 30 degrees Celsius, it's going to be twice as warm as something that's 15 degrees Celsius, right? So nominal wouldn't apply, ordinal wouldn't apply, because the differences between consecutive values or any values in the set would be meaningful. It is possible for a temperature to have a zero value. It's just a question of whether you think a body temperature can have a zero value, and that will be the determining factor of whether or not you allow this to be ratio. So I would say ratio. So this is my conclusion. It's ratio because the body need not be human or alive. I mean, if the body like a stiff at the morgue, yeah, as morbid as that is, it's in the freezer. You know, it could be 0 degrees, and we also don't know, again, if it's Fahrenheit or Celsius. But really, the point of this is not to be able to look at data and say it definitely is interval, it definitely is ratio, it definitely is not, or whatever. It's more so that you're having that internal debate of which one is it? Is it interval? Is it ratio? Because that's going to determine, and we'll talk about this next class, that's going to determine what sort of statistical analyses you're going to apply, right? Whether it's going to be a normal distribution, whether it's going to be a binomial distribution, things like that, right? So we're kind of moving towards merging the qualitative aspects of statistics and the quantitative stuff that we've been working on in a topic called inferential statistics. So that's going to be a topic of study next week. Just a reminder, a little housekeeping. I believe, yeah, next Wednesday we do not have class, right? So that's the, they call it a reading day. I don't know, colleges, they make up weird terms for stuff. But whatever, it's a day, I guess I'm supposed to read. Nah, I think it's something where it's basically the equivalent of a superintendent's conference day where I'm supposed to do work, but you don't have class, all right? But it is what it is. So we do have class on Monday. We'll continue with the content. I'll talk to you about the next technology assignment. And on Wednesday, we will not have class because that's the reading day. And then we'll pick up after Thanksgiving. All right. So at this point, I'm going to let you off the hook. So enjoy the rest of your evening, and I'll see you on Monday. If you have any questions, stick around, and be well.
Thanks a lot. Good night.
Thank you, Professor.
Thanks, Professor.
Good
Bye,
night.
Professor. Thank you.
Have a good one.
Hey, I have a quick question. So for like ordinal, how come the differences between data values don't matter?
By definition, or how come it didn't matter in the example that we chose?
No, like why don't they, like why does, I guess like I don't know what it means when you say that they don't matter.
Oh, well, what it's telling you is like, for example, if I wanted to, the example I used where I have the class roster, all the names are listed alphabetically, and every name is associated with a number. Like if I were to subtract the number associated with your name from the number associated with another student's name, what would that difference mean? You know, it wouldn't mean anything because it's just a position within the data set.
Oh, okay. And then
Yeah, it's when you're using a numerical value as kind of an indicator of position within a data set.
so
that's
it's only meaningless because you're just giving it abstract like substitute placeholder name number things.
exactly.
Okay. All right, I gotcha. All right, thanks a lot. Catch
No
you
problem.
next week.
Jake.